Welcome to this video. In high school you have worked a lot with lines in the plane, computing slopes, a line that goes through 2 points, a line given by 1 point and the slope and so on. With the theory we have seen so far on vectors, we can now start discussing lines and also planes in space, in three-dimensional space. And as you can imagine, they are incredibly important for many applications. So in this video, we will consider the following topics. Let's look at a short outline. We will look at the description of lines in three-dimensional space that is different from two-dimensional space. How you can tell whether lines are parallel and how you can define the angle between two lines when they intersect. We will also consider how you can describe planes in space. And here, just for emphasis, a plane in mathematics that extends in every single direction. So it's something that has zero thickness and it goes to infinity in all directions. If you have two planes, then you can talk about the angle between them. And finally, as a kind of application, we will give a method that when you have a plane and you have a point, how you can compute the distance between the point and the plane. That can be interesting, for instance, in computer software, if you have a wall and you have an object and you want to see what is the distance between the object and the wall. So let's first go to lines in three-dimensional space. So the way you can describe, characterize, fix a line in three-dimensional space is by giving two sets of data. One is a point that is on the line, and two is the direction vector. So a direction vector is just a vector, but what happens now is that you have a point here somewhere in space, and basically from this point you're going to travel in the direction of this direction vector that we call A here. So if you multiply A with a positive number, then you travel in this direction. And of course, a line also extends to infinity. And if you multiply with a negative number, you're going to travel in that direction. So the line itself, if you have these two things, is given by the equation that we are going to consider all points x, y, z in space that have the form that they start at the point P. And then you have some multiple of the direction vector. And again, if r is a positive number, you travel in that direction. If this number r equals 0, then you're precisely here at the point P. And if r is going to be negative, then you travel in that direction. If you think a little bit about it, then you see that this equation for a line is not unique. So for one thing, we still have a free parameter, which makes sense because we're traveling along a line and we have to specify where we are on the line. And basically this R number tells you that. But for this P, you could pick any point on the line. So if I would instead have chosen this point Q here, then I could also have used that to write down an equation for the line. So it is not a unique description. Now I can also write it in components. So if you read off, we find that x equals x1 plus r times a1. So that's what it says here. Then for the y component, we have y1 plus r times a2. And the z component is z1 plus r times a3. So that is a line in space. Now, there is something that is also interesting when we're not in 2D but in 3D. In 3D, you can have the situation that you have two lines that do not see each other. So what you have in the plane always, if you work in 2D, then you have that lines are either parallel, which means that they don't see each other, or they intersect. If they're not parallel, then they have to intersect somewhere. But in 3D, you also have the situation where they completely miss and they are not parallel. So that's going to be on a future slide. What I have here is if you have 2 points, say P and Q, specified by their components in space, then to find a line through these 2 points, you need to have a point on the line. So you can choose either P or Q, and there are many more choices, but these are obvious. And as a direction vector, what you should do is you should subtract the coordinates, because that is simply the vector pointing from Q to P or from P to Q. You can choose either of them. So say that we have two lines in space, then basically their direction vectors give you a lot of information. So say that we have a line L that has a direction vector A, we have a line M that has a direction vector B, then we call them parallel if the direction vectors are parallel. So we have seen previously when we were studying vectors what that means. It basically means that the B vector is some multiple C times A, where C is a positive or a negative number. So parallel direction vectors mean parallel lines. And this is what I said before. So in 3D, you can have lines that are parallel. You can have lines that intersect. So if they intersect, it means there is one plane going through them. And they can be skew. And skew means that they are not parallel and they do not intersect. So that's a new situation that can also happen that you do not have in 2D. Now, if you have intersecting lines, so if you have lines that do this, and they extend in every direction, this one also, but they do this, then you can talk about the angle between them. And again, the angle between the lines, simply take their direction vectors. You compute the angle between the direction vectors, that gives you the angle between the lines. And then in particular, if the direction vectors are orthogonal, we call the lines orthogonal. So that means that they make a 90-degree angle. So much for lines. Let's go to planes. Now, to introduce the equation for a plane in three-dimensional space, let's pick a non-zero vector that I call n. So very often we will say that this vector n has three components, n1, n2, and n3. So here is such a vector. If you now look at all the vectors that are orthogonal to n, then that will be a plane, because if you look at this red plane here, then every single vector that you could draw in this plane is orthogonal to n. And for that reason, n is called a normal vector of the plane. So normal means perpendicular or orthogonal here. As an equation, you find that the dot product of n with x should be 0. So for n we have that. X is a general point in space, so with coordinates x, y, and z. And then if you compute that dot product, so n with this x vector, you see that we find the equation n1 times x plus n2 times y plus n3 times z equals 0. So this is the equation of a plane that goes through the origin. As you can see, the origin here, 0, 0, 0, is part of this plane. Now, if you want a general plane in space, a plane that does not necessarily go through the origin, then you have to specify an additional point. So if you give one more point that you want the plane to go through, plus such a normal vector, then you have the full equation. So let's do that. So I'm going to pick a point P now that should lie in the plane. In the plane I call that V. Then basically what you do is you translate the normal to this point P, and then you have that every single vector here is orthogonal to this n vector. So this is the full equation. So what does that look like? Well, what you can do is that you say, well, I'm going to shift a general point in space back to the origin. So I'm going to subtract the coordinates of P. So I'm basically moving any point along this vector that points to P. So I'm moving points back to the origin. And then we're in the situation of the previous slide. So then we find that apparently the dot product of the normal with this vector, so being shifted back to the origin, should be 0. And if you write that out, then now we have n1, n2, n3. Those are the components of the normal. Times these three components should be 0. And what we have is that this n1, x1, n2, y2, n3, z1, that's just a constant. So the general equation of a plane in space has this form. The dot product of a normal vector with x, y, z equals a constant. And the constant, if it is 0, it means that the plane goes through the origin. If it is non-zero, then you have a situation like here, where your plane goes through some point in space. So this is the equation, the general equation of a plane in space. Now, if you have two planes in space, then they can either be parallel like this, or if they are not parallel, then they need to intersect. And as soon as they intersect, they will intersect through a line. So then you will have a situation like this. So we have one plane, say V1, and we have a different plane, say V2, and you see that they intersect along a line L. So as soon as two planes are not parallel, they will intersect in a straight line, and I called that L in my little picture here. Now, for lines, we could talk about the angle between them if they intersect, and then we use the direction vector of the line. For planes, we have normal vectors, and the angle between two planes is the angle between the normal vectors, and we know what that is because these are vectors, and we know already a lot about vectors. So in particular, if the normal vectors are parallel, then the planes are parallel, and if the normal vectors are orthogonal, make a 90-degree angle, then the planes are also called orthogonal. Now finally, let's look at a little puzzle like this. The distance from a point to a plane. So we're in three-dimensional space. We have a point P somewhere. We have a plane V with a normal vector. And we would like to know the distance from the point to the plane. There are different approaches how to do this. And I will give a general formula, but that may be a bit hard to remember. So I'm also going to give you a different approach that looks more at the inside, that you actually know what you're doing here. So let me give an example. First, how we can do this with what we have seen already. So assume that we have a plane V, and V is given by 4x plus 3i plus 4z equals 17. And I also have a point P, and P is the point with coordinates 18, 11, and 19. So the question is to find the distance from the point to the plane, what you see in the picture here. So basically we have a certain distance here, let's call that D, and the question is, what is D? D is a number. Now, the idea that I'm going to do first is that I say, well, okay, I have this plane. Let me draw a new picture. I have this plane V. I have my point P. And what I'm going to do is I'm going to construct a line L. With two characteristics. L is orthogonal perpendicular to V. So then I know the direction vector of the line should be the normal vector of the plane. And I want P to should lie on L. So as we have seen, I have now specified the direction and the point that lies on the line. So that gives the full description of that line. So that's going to be step 1. Then step 2 is that I'm going to compute the intersection point of L with V. Intersection point, say S, of L and V. So that's here in the picture, this point S here. And then you see, because this one makes a 90-degree angle, we have then that the distance between the point and the plane equals the distance between P and S. And the distance between 2 points, we already know that. We have already covered that. So this is my outline, my strategy to solve this question. So it may seem that it's very specific to this problem, but you will see that such an interpretation of understanding what you're actually doing will help you solve many of these questions. And then afterwards, I'm also going to give a general formula. But let's first try to do these steps. So first, I need to have a line that is orthogonal to L. So what that means is that the direction vector should be the normal of the plane. And the normal of the plane, if you have an equation of the plane, you can immediately read off the normal vector. So it's very easy to find the normal vector. You just look at the coefficients of x, of y, and of z. So 4, 3, 4 is a normal vector of the plane. So we have that n, the normal vector of the plane, is 4, 3, and 4. And I should pick the line L as this is a point on the line, plus any multiple of this direction vector, and then I've found L. So let's go to the next slide. So step 1, that was to find L. So L are all those points x, y, and z that are the point P that I want to be on the line. So that's 18, 11, and 19, plus any multiple, let's call that lambda. Lambda is often used for that Greek letter for L. 4, 3, 4, and lambda can be any number. So this here is now the direction vector. Direction vector. If lambda is 0, we're precisely in the point P, and otherwise we're traveling along the line L for different values of lambda. By construction, L is orthogonal to the plane. Step 2. Step 2 is to find the intersection point. So step 2 is find S. And S was the intersection point of the line with the plane. The way you do that, well, we know that the plane has the equation, or was it 4x plus 3i plus 4z equals 17. Now, these points are all the points that are on the line. So basically what I need to find is the lambda value for which L intersects the plane. The way you do that is that you say, well, my line L, I can also say that's x equals 18 plus 4 times lambda, y equals 11 plus 3 times lambda, z equals 19 plus 4 times lambda. And what I'm going to do is I'm going to take this x, y, and z. I'm going to plug those into this equation, and that gives me one equation for lambda. So what do we find? We find 4 times 18 plus 4 times lambda, plus 3 times 11 plus 3 times lambda plus 4 times 19 plus 4 times lambda equals 17. Now, if you compute that, I'm sure you can do that. So you just multiply everything and then you solve for lambda. You are going to be finding lambda equals -4. And then we can compute s, because if we know that lambda is -4, we can compute x, y, and z, and those are the coordinates of the intersection point. And that's going to give you s equals 2, -1, and 3. And then the last point, so step 3, I'm going to squeeze that in the corner here. That's just going to fit. Step 3, you have to compute the distance between P and S. And if you do that for, we know P, we know S, you will find this to be 4 times the square root of 41. So not a very pretty number, but at least decent. So that is the first way on how to solve this question. Given a plane, given a point, just construct the line that goes through the point, is orthogonal to the plane, find the intersection point and the distance between them. So quite a few steps, not very difficult if you look at the individual steps. So what you should have is an idea of what you need to do, a kind of plan, which steps you need to take, and then just carry out your plan. I already said that there is also a fixed formula to do this, and I'm quickly going to sketch how that works. So the way that works is that you say, well, okay, I have this plane here. So in the example, we had 4, 3, and 4 here for the normal vector, and this one was 17. And we have a point, so in the example it was 18, 11, 19. And now what I'm going to do is I'm going to say take any point in the plane. So here I just took a point Q, so not necessarily the projection, the orthogonal projection of P onto the plane, but I'm going to take any point Q with these coordinates and let A be the vector from Q to P. So here is a point in the plane, here is P, and this vector A here, this red vector. You can find that now. And then the idea is that the distance that we are interested in is the length of this vector. So I'm going to decompose this red vector into a component orthogonal to the plane and a component in the plane. And if I then compute the length of this vector here, then I have the distance. And we know how to do that because we already solved that problem before. This is precisely what you get if you use the formula of the component of A along N. So we have seen that when we were studying dot product, that we could find the length of this vector as the component. And if you work that out, this is precisely the distance that you get there. So as I said, you can use this, but it means that you have to learn this formula by heart. And the construction with the line may be easier. So that would have my preference, since that is something that I can remember also over a longer period of time. And this formula, well, I forget that if I do not use it regularly. So just as an overview of what we have seen, when you want to describe objects in space, you can have a point, and a point does not have any free parameters. You give an x, y, and z coordinate, and that is some point in space. If you have a line, then we have the vector equation that we are interested in all points x, y, z. And then we have that this is some point that is on the line. And this here, this 1, 0, 1, is the direction vector. And there is still 1 degree of freedom. So lambda can be any number. For a plane, you can either give an equation in this form, and then you can immediately read off the normal as 2, 1, and -2. You read off the coefficients of x, y, and z. Or alternatively, you say, well, this is going to be some point that is in the plane, and I'm going to specify 2 direction vectors. So these are 2 vectors that are in the plane, and these lambda and mu can be any number. So you can go from this vector equation to this equation. And to show you how to do that, let me get a little bit of space. So I'm going to show you how you can get from the vector equation to the last equation. So what we have is, 1 second. So we had the vector equation, so plane with vector equation x, y, and z. And the example I had on the previous slide is that we take 1, 2, 3. Sorry, that was a bit too enthusiastic. 1, 2, 3 plus some number lambda times 1, 0, 1 plus some number mu times 3, 4, and 5. And basically what you see is that for a plane you still have 2 degrees of freedom. So for a line you only have 1 degree of freedom where you are on the line. In a plane basically you could pick 2 directions in which you can travel, and for both directions you have to specify how far you travel. If I write this out, I find x is 1 plus lambda plus 3 mu. I find y equals 2 plus 4 mu, and z equals 3 plus lambda plus 5 mu. Now the idea is I have 3 equations. In these 3 equations I have x, y, z, and lambda and mu. Let's kick out lambda and mu, and then I'm left with an equation that only has x, y, and z into it. So for instance, you could pick the first equation and the last equation, and then if I subtract them, I find x minus z equals 1 minus 3 is minus 2. The lambda drops out, that's why I do it like this, minus 2 mu. And I still have the equation I just copied that, y equals 2 plus 4 times mu. And you see if I now multiply the top equation with 2, then I have 2x minus 2z equals minus 4 mu. I copy the equation for y. And if I now add them, then the mu drops out. So I find 2x plus y minus 2z equals minus 2. So apparently this is an equation for the plane. There are other ways how to do this. For instance, what you could also do is you could say, well, this is a vector that is in the plane. This one also. So if I now compute their cross product, then I find a normal of the plane. And then if I also use that this thing is in the plane, then I can also find the full equation. So that would be an alternative. First compute the normal and then the full equation for the plane. Let me leave it at this for the moment. There are many questions on how to deal with lines and planes. You will have to try and solve them. If you cannot imagine, let me know. I will add more examples. For now, let's wrap up this video and make a short list of what we have studied. So what we have seen is how you can give an equation for a line in space, basically by providing a point that is on the line plus a direction vector. We have seen that if you take 2 lines in space and they intersect, that you can compute their angle by using the direction vectors of the lines. We have looked at planes, and also if planes intersect, how you can compute the angle, and we have studied how you can compute the distance from a point to a plane. That's it for this video, and I'll happily see you in the next one.